Hello, Algebra 2. Today we're going to be looking at Section 12-2, Statistical Analysis. This continues our unit for statistics and probability. Our objective is to determine which measure of central tendency best represents a set of data and to calculate standard deviation. So let's first talk about measures of central tendency. Measures of central tendency. We have three main measures. We have the mean, and the mean is the average. And we calculate the average by taking all the data 1 plus data 2 plus data 3 plus data 4, and so on and so on and so on. We add up all the data and divide by the number of data points. And most of you learned this at some other point, but just in case, I'm going to write it down. We are going to use this. We got to know when to use these. That's going to really be our main focus here. We're going to use the mean when there are no outliers. Okay, and if you remember an outlier, if you know what that is, great. If you don't know, an outlier is a piece of data that doesn't fit the pattern. Okay, so this happens quite a bit. This happens in test scores and stuff like that, where somebody's consistently getting like 80, 81, 82, 81, 83, 81, and then all of a sudden they get a 60 because they didn't know that material. And so that 60 would be an outlier if we were looking at the average score for the tests. Okay, the next one is the median, and the median is the middle number when we put them in order, or the average of the two middle numbers if you have two numbers in the middle, which happens if you have an even amount of pieces of data. And this is best, we're going to use this when we have outliers but no big gaps in the middle of the data. And when we're doing this, we have to put them in order, usually from least to greatest, but that doesn't really matter as long as they're in order. So that's when you would use the median. And the last one is the mode. And the mode is the number that occurs the most. So, for example, if I was going to take the mode of homework assignments, you either get, as we've been working through the year, you've either gotten a 5 or a 10 on all homework assignments. You either did it or didn't do it, essentially. A good way for me to figure out your grade on homework assignments would be to take the mode of it, which would either be a 10 or a 5, whichever one happens the most. And that's exactly when you're going to use this. You're going to use when the data repeats a lot. Not necessarily every time, of course, but you're going to use this when the data repeats a lot. There is another concept here if you're looking at the study guide, and it's called margin of sampling error. And this is a way of measuring how well a sample represents the whole population, how off you are. And to calculate it, you do plus or minus 1 over the square root of n for n items in a random sample. And I talked about it being very important that things are random in the last section. It's still important here. And this is where you get, as we talk about elections, this is where you get the so-called sample error for elections. Somebody's up by 6 points in the polls, plus or minus 2 points. And this margin of sampling error is where they get that idea. It tells you how accurate your data is, tells you how well you're able to predict things. If you're predicting, say for example, that you're going to get a 72 on a test, and your sampling error is plus or minus 30%, then it really doesn't mean a lot, right? So that's what we mean by that. I'm not going to talk about that much more, but I wanted to put it there. So our first example is a question which measure of central tendency best represents the data and why. So let's give you some data. They're usually done in these squiggly brackets. Let me give you a set of data. 2.1, 21.5, 22.3, 22.8, 23.1, and 159.4. So let's look here. What about the mean, the average? Well, if you look at this, look over here, we got this 2.1, and over here we've got this 159.4. And in between those, all the rest of these are 21, 22, 23. So these two are exactly what we call outliers. And when you have outliers, you don't want to use the mean, so we're going to throw the mean out. What about the mode? The mode happens when we have repeating stuff. So look in here, amongst all this data, I don't have one repeating number. So that tells me to throw out the mode, leaving me with probably the median. And so let's confirm that. Let's see, we have outliers, and that's okay with using the median. What you want to do in the median is you want to have them in order, and you want to look at the middle. So here, this would be the middle. Sometimes you have 2 in the middle because of that. And all that happens is you take the average. So we'll calculate that. But certainly, we don't have in the middle here amidst all of these ones, we don't have any big leaps. We go from 21.5 to 22.3 to 22.8 to 23.1. We're slowly getting larger, but slowly, and we're not like taking big steps forward. So all of that tells me that the median is indeed the one that I want to use. And then if I wanted to calculate the median, I do 22.3 plus 22.8 and divide it by 2, and I can do that real quick. By the way, I'm going to use Desmos, not with a capital D. I'm going to use Desmos.com as my calculator. It's a nice little online program, just a thing that you can go to and use, and it lets you keep track of all of this. So you hear me typing here, and that's me putting this into Desmos, and that gives me an average of 22.55, and so that would be my calculated median if I needed to know that, if I wanted to know that. So the median is the good one for this, and all you're going to be doing in the problems for this is deciding which measure of central tendency to use. Okay? So now let's talk about the one that takes some much more intense calculation, and that is standard deviation. Now, we're not going to see the use of standard deviation, that is, what it's good for, what its basically its main use is, until the next section. But standard deviation is incredibly useful. It really helps us to know how far apart things are and how our data evens out, basically. But for right now, we just want to talk about how to calculate it. And we've got two different things. We've got for samples. And a sample, and we'd love it to be a random sample. A sample is part of the whole. That is data that we're taking that is not everything. Okay? And so when we just have a sample, first of all, we're going to use a lowercase s to calculate it. And the standard deviation will be this pretty big formula here. It's the square root of all this weird stuff here. And actually, let me do it down here where I can do it a little bit easier. So it's the square root of x sub n minus x bar. Well, let me not do x sub n. That's for one. X sub 1 minus x bar, all of that squared, plus x sub 2 minus x bar, all of that squared, plus x sub 3 minus x bar, all of that squared, plus, and so on and so on and so on. All of that divided by n minus 1. So now I got to tell you what this is. So I'll put in a little box up here. X sub 1, x sub 2, and so on and so on and so on. These are the data. Okay. So x sub 1 is the first piece of data, x sub 2 is the second piece of data, and so on and so on and so on. X bar is the mean. It is the average of all the data. Okay? So this formula, as you can imagine, gets very big very quickly. It's a pain in the rear, but it's incredibly useful, and that's why we have it. Now, let's talk about for populations. And our notation is going to be a little bit different for this. A population is, of course, all the data of the whole thing which a lot of times is not possible. It's rare to be able to get data for the population unless you have a small population. We could do it in a classroom. If we had everybody there on the same day, we could take a population instead of a sample. If we were missing one person from the class, all of a sudden it's a sample. Okay? So it's when you have the entire population, you get this little symbol here, and the way that you calculate the standard deviation for a population is similar. You do x sub 1 minus, this is called mu here, plus x sub 2 minus mu plus over and over and over. These all get squared, by the way, over n. Okay? Oh, and I didn't tell you what n was in the last one. The x1, x2, x3, and so on are the data, again. Mu, the Greek letter mu, by the way, that mu is the mean of the data, and we change it up just because we're talking about population here. N is the number of pieces of data. Okay? And I want to show you again the difference between them. Some of the things on the top, it's just a notation difference, okay? But it's always the data piece minus the average and all of it squared and all of those added together. Now, when you have a sample, you take one less than the total number of data sets, and what this does is it helps account for error. But in a population, you don't need to account for error, so you just use the total number of data, of pieces of data, okay? So this then brings us to, how do you find this? How do you discuss this even? So this will be our second example. Couple of things we want to know here. Is it a sample or population? Find the standard deviation to the nearest hundredth. And that is going to require a calculator. So here's the data. It is the test scores for 12 students in a college math class. So, is this a sample or a population? And I got to give you, let me give you all of the data here. We got a score of 61, 99, 75, 93, 92, 69, 77, 94, 73, 65, 98, and 91. And the question then is this a sample or a population? That's our first question for this data. So if it was a population, then there would only be 12 students in the entire class. That's not very probable, although the wording is a bit ambiguous. It doesn't tell us whether that's the whole class or not. But usually this would be such a small class you couldn't even have it. So this is probably a sample because the class is quite probably larger than just 12 students. So we're just looking at a sample here, okay? The next one is to calculate the standard deviation for this class, and we're going to do that by using this formula where we do all of these things, and this is going to be a very long problem because we've got 12 of them to do. We're going to do x1 minus the average squared plus x2 minus the average squared plus x3 minus the average squared plus more and more and more until we get to x12 minus the average squared, all of those squared, and then we're going to divide it by 12 samples minus 1, so 11. So that is quite a bit of work, and I'm not going to ask you to do that much work, but I am going to take you through what it would be. So the average would be, we add all of these up, and if you add them all up, you get 977, and there are 12 of them, and when you calculate that, you get 1.42 as we round it to 2 decimal places, that is to the hundredths place. And then when you do this, and I'm going to add them all up for you, okay? And when you do all the addition, you get 2,095.55 when you subtract them minus this and square them. This is what you get over 11, okay? And I'm going to put that into Desmos, and we're going to see what we get. And when you put things in Desmos, again, this is desmos.com, to do the square root, you use SQRT, and the square root symbol will pop up. So I typed in SQRT, and it gave me the square root symbol. And then after that, I'm going to do a fraction, this divided by this, and that's all going to go right inside that square root. So 2095.55 over divided by 11 gives me approximately 13.80. That 0 is important, by the way. 13.80 as my standard deviation. Okay? And this is percent, I assume, because we're talking about test scores. But a 13.80 test score is the standard deviation between test scores. And again, that doesn't mean a lot to you yet, but it will. On the work that I'm going to ask you to do, I'm going to give you a 6, okay, 6 data pieces. And that's going to be plenty enough for you to have to figure out. Okay? Thank you, guys. I'll see you later. Bye.